So in FRQ number 5, we're going to be looking at a data table with information gathered by hanging different blocks of different masses on a vertical spring. And here we see that it gives us mass, weight, and x. Mass is the mass of the spring, and the weight is the force of gravity of the spring, which is also the force acting on the force of gravity of the block, which is the force acting on the spring pulling it down. And then x is the distance measured in meters from the equilibrium where the spring sits if there's nothing hanging on it. And part A asks us to draw an appropriate graph that is associated with Hooke's law. So I'm going to draw out the vertical and horizontal. So we know that Hooke's law is going to be is measured as newtons per meter. So on the vertical, it's going to be force in newtons. And then on the horizontal, it's going to be the distance from equilibrium measured in meters. So if we graph the points that the table gives us with the weight acting as a force, we have at 0, 0, and then at a force of 0.98 newtons, the spring extends 0.025 meters. And at a force of 1.96 newtons, the spring extends 0.050 meters. And then at 2.94 newtons, the spring extends 0.076 meters. And then at 3.92 newtons, the spring extends 0.099 meters. And then at 4.90 newtons, the spring extends 0.127 meters. So the force, again, is just the weight of the block, the varying weights of the block that hang on the string. So if we plot the points, we'll get, well, this is supposed to be a straight line, and this is going to be, the line represents the spring constant, because spring constant is written as newtons per meters. So spring constant in newtons per meters. That line represents the spring constant K. And for B, it says determine if the experimental data follows Hooke's laws. So to do that, we have to see if the spring constant is actually the same for each data set. So if it gives us that 0.98 newtons of force is over 0.025, extends the spring over a distance of 0.025 meters, we'll see what constant that gives us. Divided by 0.25 is about 39.2 newtons per meters. That's the spring constant for the first set of data. And then on to the next one, 1.96 newtons of force extends the spring a distance of 0.05 meters, and that gives us again 39.2 newtons per meter. So far the spring constant, this is the spring constant, is the same. And then for the next one, it's 2.94 newtons of force extends the spring 0.076 meters, and that gives us 0.076. A slightly different number at 38.7 newtons per meters, and then 3.92 newtons of force over extends the spring a distance of 0.99 meters, which gives us 39.6 as a spring constant, and then 4.90 divided by 1.127, 4.90 newtons of force extends the spring 0.127 meters, which gives us 38.6 as a spring constant. And these numbers are slightly varying, but if you round up a bit, they all average out to like about 39 newtons per meters. So we can, with just a varying amount of difference, we can conclude that the spring does follow Hooke's law with the spring constant of 39 newtons per meters. And then moving on to part C, if a 0.8 kilogram mass is used, how far will it stretch the spring from its initial resting position? So we saw here where mass is given here. So to convert mass into a force of gravity, we'll multiply 0.8 kilograms, which is the mass given, times gravity, which is 9.8, which will give us 7.84 newtons. That is the weight of the mass and also the force now acting on the spring. So if following what we have here, 7.84 newtons, we want to know how much distance the spring extends in meters, and we have a spring constant given to us as 39. We round it up to that. Then we'll rearrange to solve for x. So we move x to this side and divide both sides by 39. We'll get that x equals 7.84 divided by 39. We'll get that x equals 0.201 meters. So with the mass of 0.8 kilograms on the spring, it will extend 0.201 meters from its equilibrium point at 0. So for D, it tells us if the 0.1 kilogram mass is stretched an additional length of 0.082 meters from its equilibrium position, and then release, calculate the speed. So when the mass is on the spring and it has already settled, like once it's already settled, this is its new equilibrium point. So if we're looking at the 0.1 mass, we'll say that its new equilibrium point is 0.025, which is also stated here. So if it's stretched an additional length of 0.082 meters, that will give the spring a potential energy that when it goes back to the equilibrium point at 0.025, there will be a kinetic energy. We can use that relationship to solve for velocity. So let's say that Ke at equilibrium, which at equilibrium is equal to the potential energy of the spring, which is created when it is stretched a distance of 0.082 meters. So if we break down kinetic energy, we know that it's 1/2 mv squared, and that's going to be v at equilibrium. And the mass is the mass of the block given for part D, which is 0.1 kilograms. And PE spring is 1/2 kx squared. So kx squared, yeah. So we'll plug in what we know now. So 1/2, the mass of the block for that part would be 0.1 kilograms. And then V equilibrium is what we're trying to find, equals 1/2. The K spring constant of the spring is 39. And then the distance stretched, it told us additionally from equilibrium, is 0.082 meters. 0.82 meters. So now we want to solve for V equilibrium. So we're going to divide both sides by 1/2, 0.1. And then we're going to square both sides. So V equilibrium equals, we'll calculate that to be 0.5 times 39 times 0.082 divided by 0.5 times 0.1. Oh, sorry, I forgot about the square here. There's a square here where for the 0.082. So we put that in a calculator again. 5 times 1. That'll give us that the V equilibrium will be 1.624 meters per second. And this is the velocity once it goes back to where it was resting at 0.025. That's part D. Moving on to part E. It asks us again to do what we did in part E, except this time the distance will be stretched 0.164, which is double the distance it was stretched in part D. So again, we'll set up kinetic energy equilibrium equals potential energy of the spring when it is stretched a distance of 0.164 meters. So we'll break that down. 1/2 mv equilibrium squared equals 1/2 kx squared. Plug everything in. The mass is still 0.1 kilograms, and the v equilibrium is what we're trying to find, equal to 1/2 k is still 39 newtons per meters, and the x given to us in part E, the length that is stretched from equilibrium is 0.164 meters. We square that, and then again we're solving for v equilibrium, so we move all of this to the other side, or divide both sides by it, and then we also square both sides. So that'll give us that the v equilibrium when the string is stretched a distance of 0.164 meters is given as 0.5 times 39 square root. That'll be v equilibrium now when the string is stretched 0.164 meters is 3.238, or round it up. So that is the new v equilibrium when the string is stretched 0.164 meters for part E. And then part E also asks us to clearly state the relationship between the distance stretched and the maximum velocity at the equilibrium position. So if we look at this equation again, it gives us 1/2 mv equilibrium squared equals 1/2 kx squared. So the 1/2s cancel out, and the m and the k are always going to be constant, just depending on what's given to us. So we can technically cross those out too, because we won't be looking at those. And the relationship we want to see is v equilibrium and the distance stretched. And see, if we square both of them, the relationship will be proportional. So if the distance is doubled, then v equilibrium will also double. Proportional relation. Yeah. Okay. So that is it for FRQ 5.